Hi, so this is a video about doing analysis on engine oils, and I think there's three properties I'll think about. I'm specifically thinking about electrochemical. I'm specifically thinking about ceramic thick film printed electrodes. Don't think that all of these electrodes are actually going to be degraded by engine oil. Some of these are actually quite robust. They're made at 850 degrees C. They can withstand organic solvents quite well. This is a gold one. His fabrication temp, he's on ceramic. He's made at 850 degrees C, so he's kind of intrinsically quite robust. There's a platinum equivalent of him, again made at very high temperature, good resistance to organic solvents. So I'm thinking about these kind of thick film electrode systems being used for engine oil analysis, and I'm thinking there's sort of three ways of analysing an engine oil. I'll think of a scenario like a degradation. I want to monitor the degradation of an engine oil. One way of doing it, these are all opinions by the way, is conductivity. So you could have now these are spirals, but spirals are really just lines of electrodes. So we have these kind of spiral electrodes. So we have sort of two lines, and we've just wound them up into a spiral. So it's a very efficient way of having effectively two line electrodes. And we're saying, okay, so you have these two lines, and you could use them to measure the resistance or conductivity across those two electrodes. So I'd sketch up the kind of thing that I would expect, so I would expect, if I was monitoring an engine when the oil was fresh, maybe I would expect a sort of signal conductivity, if you want to call it that, with time. Maybe as the metal content went up, the conductivity of those solutions might also go up as well. So you kind of get, this kind of trending upwards. So maybe looking at the conductivity or impedance or resistance of engine oils is a way of monitoring them using these types of electrodes, and they're parallel electrodes, or maybe again these are parallel electrodes, they're just in a spiral, would be a way of doing conductivity. Another idea is looking at the electrochemical or looking at the molecules in that engine oil and sort of characterizing those molecules as a function of time. Now I think they put some imidazoles sometimes, but I'm basically just trying to think of molecules that are sometimes in engine oils that are electrochemically active, and you get molecules like an imidazole, I believe, are added. So if somebody gave me an engine oil and said sort of characterize it electrochemically, I would be tempted in the first instance to take one of these electrodes and actually put a sample on it and do a cyclovoltammogram and see what I got. Now I'm just going to sketch, some ideas, what would I potentially get. So I have voltage and I have current here, and I would sort of scan it, and I would get, if I was lucky, I might get some oxidation peaks. Maybe I don't get the re-reduction, maybe I get something down here, so it's quite, ugly in some ways, but, I have some electrochemical activity in that engine oil. Now, it could just act like a big resistor, and in fact, you don't get nice CVs. You just get something that's really quite, you scan voltage up, the current goes up, you scan voltage down, and the current goes down, and you kind of get something that's fairly ugly, let's say, but it's just acting like a resistor, basically, the engine oil. Now, the earlier idea about if they're like a metal particles coming into that engine oil, you might find that this gradient decreased in fact, increased. We got more current per voltage because the resistance had gone down. So you might find this gradient changed as a function of time because the resistance went down. Now, that's so I'm sort of saying, you could use these thick film electrodes to maybe look at the conductivity of these oils, maybe look at the electrochemistry of those oils, but sometimes they might be very boring and there's actually nothing, you can't discern a molecule, or you can't discern clear features, you just get these straight lines. So that might be the result of that. I am thinking actually, we have electrodes that look like this, and I might suggest not using these big electrodes because of a problem called IR drop, that if you try and push large currents through oils, you'll just get you'll just have basically measuring quite a large resistance, and you'll lose all the features. So sometimes I'll mention the micro and mini electrodes that we have, which might give you more features, whereas a macro electrode would give you lots of big signal that looked like a straight line. If you do a CV in a micro electrode, you might end up with a bit more of a feature, which would have got lost on the macro electrode. So trying these mini and micro electrodes might be an idea. I want to get specifically now onto maybe measuring the pH of oils. On this one, I think my first attempt would be to use a carbon electrode. Maybe this one here. Now, this is speculation a little bit, but I'm thinking about a carbon electrode. It could have in the carbon, it can have functionality like this quinone or this orthoquinone. These kind of molecules, if you have these present, if I did a CV, if these were on the carbon surface, I would expect a CV like this, that you would kind of come up, not really get much activity. When I came back down again, I might get a reduction peak, and then when I came back up again, I would then get a sort of oxidation peak. Now, I'm thinking, if your surface has these kind of moieties on it, these peaks will be pH sensitive, because the reduction of that is going to, or either of these is going to require 2 hydrogens plus 2 electrons. So there's actually, in its peak position, you need these protons, and therefore the more protons are in there, or the less protons are in there, i.e. the pH, then these peaks will shift. So that is the idea of using the intrinsic electrochemical activity of the carbon electrode, and you're looking at the peaks associated with the electrode, and you're kind of saying to yourself, all right, pH in my sample, which is oil, is shifting the peaks. Now, people would say to you, the problem with these is that there's a reference electrode on there that is silver chloride, but of course you're running silver chloride in oil, so it's not a silver chloride. There's no chloride around there, so that pH sensor, that reference electrode is not in its native environment. It's not going to behave the way you would expect. It might be good enough, but there's a lot of mights in here. You have to try things out. Is my comment. You have to try. If you don't try, then there's no point. So one idea is to actually, if I was going to measure pH, would be to use the carbon electrode itself, maybe deliberately oxidize it to make sure I had lots of these groups on it, and then watch the peak positions and see if that was a function of pH. You could actually modify carbon electrodes. I would cast down this molecule onto the surface. So if you don't think there's enough of these molecules on the surface, I would cast this guy down. I think that's, yeah, that's anthraquinone. Anthraquinone. So he's probably likely to want to, he'll absorb well onto the surface of the carbon. It's interesting, if I was doing that onto carbon and then using the electrode in an aqueous solution, I would be pretty sure that that would stay on the surface for quite a long time, because lots of aromatic structure here, it would stick well to the carbon surface. Of course, in oil, it might come out off, so there's that's something that has to be investigated. But it's worth a try. Is you put that deliberately, you cast it onto a carbon surface, and if you do that, you once you've optimized, you'll be able to do CVs. Like if I scanned up with positive on the first one, I wouldn't get it. Then I'd get some sort of reduction, and then I get an oxidation. And again, the oxidation reduction of that is pH sensitive, which you'd see in the peak position. Now, basically, there's I put lots of ifs and buts and things that could go wrong. My suggestion is to go for it. I would suggest what I'm going to do. I'm going to do a second part of this video when I'm going to then go through all the different types of electrodes from Zimmer and Peacock, and talk about the strengths and cons depending on whether you're trying to measure conductivity, redox active molecules in the oil, or pH. Okay, so this is the second part of this video now. Okay, so in the first part of this video I talked about potentially measuring an engine oil or an oil in three ways. Conductivity, impedance and resistance of the oil, i.e. its electrical properties. The second way was, are there any electrochemically active species in that engine oil? And then the third way is, if you want to measure the pH of the engine oil, could we use the electrode surface, if it was carbon? Are there pH sensitive molecules on that surface that we could use to indicate the pH of that engine oil, for example? So let me start off with the idea of measuring an engine oil's conductance. To measure conductance, conductance, resistance and impedance are actually measured are often measured using two parallel electrodes. We've got some certain electrodes that are quite resistant to organic solvents, so those are the ones that I would obviously recommend just in general for engine oil analysis. So I have a bare gold one here. It's a spiral. That would be a good one to try out for measuring the, let's say, the conductance of an engine oil. We have that in a carbon version. I'm specifically going to these ones that are resistant to organic solvents because they've been formulated to be good with organic solvents, which will make them better to things like engine oils. And then I'll show you that there's a platinum equivalent. And even when I go to the platinum, there's ones that are specifically made for organic solvents, and those would be the ones that I would recommend. Effectively, these spirals are two parallel electrodes that have been wrapped up together. So you would you're asking the question, what's the impedance, resistance, or conductivity between those two electrodes, and does that sort of change as a function of time as the engine oil wears and the engine wears? Can I see that that change? I strongly suspect the answer is yes. Now, you can actually also, we also have these kind of parallel electrodes as well, so they'll do a similar job. I kind of like these because if you use these parallel electrodes in conjunction with one of our flow cells, I'll just show you accessories. There's a flow adapter, so I'll just show you it's on this page. You can end up having electrodes that are in the flow stream or perpendicular to the flow stream, and I think that will give you basically different types of signals. And whether it enhances or reduces a signal, you kind of have to try it and try it out is my suggestion. So I'll go backwards a bit and say, every time I show you a spiral electrode, there's actually these parallel electrode equivalents as well. So I said there were potentially three ways of looking at an engine oil: looking at the
intrinsic intrinsic electrical properties of it, i.e. its conductivity. The second way of looking at an engine oil, are there molecules in that engine oil, like additives, that are electrochemically active that could indicate the state of the engine oil? I mean, I know I've seen literature where there's imidazoles. There are molecules in there that might be electrochemically active. You know, I do put the word might in there. It needs to be discussed a bit more. But if I was going to try and do some cyclovoltammetry on an engine oil, you can try the gold, the carbon, and the platinum. And I would suggest the mini and micro electrodes, because if you use a macro electrode, you will end up having a lot of IR drop, which will distort any features. So it's good to have a smaller electrode, so you have less current, but it also means you have less IR drop, and you might be able to see features that you wouldn't have otherwise seen. So I would suggest this guy, for example. That's about 400 microns in diameter, that electrode. What I'll do is I'll go to the data sheet, show you where it is, and then you can get a sense that we have these these mini and micro, 400 microns and 200 microns. So these would be good ones to do the CVs on, cyclovoltammetry on, or differential pulse, however you want to do it. Now, I'm now going to go to the idea of measuring pH in an engine oil. I think you can measure pH in... One idea is to take a carbon electrode, and use it potentially in the first instance unmodified. So, you know, what I would do in that experiment is this. I would take an electrochemical sensor. I would take the carbon electrode, and I would try doing just a CV of it in the engine oil, probably this guy here, a CV of it in the engine oil, and seeing if I saw features that were sensitive to pH, and see if those peaks moved with the pH. So that if it didn't work, I would use something like anthraquinone. I would modify the surface with anthraquinone. I would just cast it onto that surface, let it dry, let it stick to the surface, and then use the anthraquinone peak positions to indicate pH. So I would use a carbon electrode. I would either use it unmodified, first of all, just to get a sense of if that was working. If it wasn't working, I would add anthraquinone. The other way of modifying the electrode is actually to put it in something like an aqueous solution, hold it at a high positive voltage, and deliberately oxidize the surface, and then use it back in the engine oil. So you try to turn some of the carbons into carbon oxygen moieties that were pH sensitive. So in summary, I quite like the idea of using these types of electrodes for monitoring engine oils, because the ones I'm showing are designed to be resistant to organic solvents, so they stand a good chance to be resistant to engine oils. They're a low-cost way of making sensors. You know, it's not like you're on a manufacturing route that's really never going to scale. Maybe to give you an idea of why, you know, this would be, let's say you had an electrode like this, and it was good at measuring pH of, you know, sorry, I'll just close that. It was good at measuring pH. What I would say is, go to the knowledge base, go to our online calculators, go to sensor and cartridge pricing. So I'm going to pretend now that I've actually found a way of monitoring the pH, the conductivity, or electrochemical active molecules in an engine oil, and I want to tell my project sponsor or somebody that how much it's going to cost. So let's pretend that you were using one of our mini electrodes. So there, the working area of that mini electrode, we've got in a ceramic that's about 30 millimeters by 10 millimeters. Realistically, you didn't need that in an engine. You know, you really needed maybe a piece that was 5mm by 5mm, let's say. And then, because it was for like a car, monitoring a car or something like that, you were going to effectively make high volumes of that sensor. And then, you know, somebody would ask you how much do those sensors cost, and you would say 6p each, or 8 cents, or, you know, euros as well. So that's just why I quite like using these ceramic thick film electrodes for monitoring oils. And I mean, and many of these ones I've talked about are actually manufactured at 850 degrees C, so they're really quite robust. And the ones that I've been highlighting are also designed to use an organic solvent, so they've got that resistance. There is a gap between what we've got and what will work, and the gap is somebody has to do that R&D and that research. But these are some of my thoughts around this. My suggestion is contact us. We're quite easy to contact. This form comes straight through to me, so fill out the form and I'll basically get online with you and have a chat. Okay, I hope that helps.